All right, let's take a look at this apportionment problem. We've got a small nation, it's got 4 states, and the population is given in each below. Now, a quick thing, the version that you have at home is a different value for each one of those populations. We have to make a small change for a couple of interesting reasons, but we're going to use 30 for A and 46 for C. We've got a total of 10 representatives to be apportioned here. So first things we got to do is we got to take our population. Okay, and we're going to take our standard divisor, that's going to be equal to the population divided by the number of representatives that we have. So that's the 200 and the 10, and we end up with a nice 20 for our standard divisor. Okay, so for each one of these, we're going to take our population and divide it by that standard divisor and fill in the values. So I get 1.5, 1.85, 2.3, and 4.35. Okay, the next thing that we're going to do is we're going to take each one of these values and we're going to round each one down, because Hamilton's method means we're just going to round down. All right, so rounding down, 1.5 just becomes 1. That becomes 1, that's 2, and that's 4. And if we add all of these up and sum across, what we find is this only gives us a total of 8, which means that we've got 2 left over, right? We've got 2 left to assign. So we're going to take the fractional remainder. This is why it was interesting earlier. The fractional remainder is just the decimal portion that we got off of each of these. And the earlier problem, we actually ended up with 2 that were tied. Okay, so now we have 2 votes to assign, and we're going to give them to the 2 highest values. So that looks like that and that are the 2 highest values. So that's going to be a 2, that's going to be a 2, that'll be a 2 because we just keep our minimum quota, and 4. When we add all of these up, we get 10, which is exactly the number that we needed. All right, next up we have ourselves the Jefferson method. Jefferson allows us to adjust things. So we're going to, instead of modifying doing a round down process, we're going to use this modified quota. The problem is we have to make sure that it adds up to be exactly those 10 representatives that we needed again. So let's start off, and if we try out 20 for our divisor, what we ended up with before was we had a 1, 1, 2, 4, which only gave us 8. So this didn't work out, so 20 doesn't work. If we try out 19, what you're going to do is you're going to divide each one of these, like 30 divided by 19, and that gives me something like 1.57, and then 37, that's going to be like a 1.947 something or other, and then like a 2.421, and then like a 4.5789, and then we're going to go ahead and do our round down process again, so we get like a 1, 1, 2, 4, and we still only get 8. So I'm going to try at 18, and let's see, that gives me like a 1.667 repeating, so that's 30 divided by 18, and then 37 divided by 18 gives me something like, what are you, 2.05 repeating, and then 46 divided by 18 gives me, what are you, like 2.5 repeating, and then 87 divided by 18 gives me 4.83 repeating. Do my round down process, and I got to 9, so that's a little better. But we're going to dive in, and we're going to use the 17. So 17 gives me a 1.76, and then some other stuff. We'll see if it matters. 2.176, and then that gives me a 2.70, let's call it 6 because they're rounded, and 5.1176. Okay, so again, I just took 30 divided by 17 and gave me this. I go through, I do my rounding. That's a 1, that's a 2, that's a 2, that's a 5, and what we end up with is this adds up very nicely to 10, and that's my apportionment. All right, let's take a look at Webster's method. Again, I still only have those 10 representatives to do. Webster does a nice thing, though. It allows us to round either up or down, and we're going to be modifying our quota. So, I mean, we might as well try out, just let's see if 20 works. And I'm going to do 30 divided by 20. That from before that gave me a 1.5. That was a 1.85. I'm going from earlier work, by the way. 2.3 and 4.35. And now I'm allowed to round up or down. So 1.5 rounds up to 2. You don't get to choose. You're just using that rounding up or down as opposed to just the round down effect. So 1.85 rounds up to 2, 2.3 rounds down to 2, and that rounds down to 4. Add them up. I got to 10. There we go. That's exactly the setup that we need for the Webster method. And let's not forget about the Hill-Huntington method. Now, Hill-Huntington lets us round up or down. Either one of those is okay, but in order to make things a little bit fairer for small states, we're going to use the geometric mean to decide where to round instead of using just the arithmetic mean from before. So here, let's try out the 20. If it works out, then everything's great. And from earlier work, it was 1.5 and 1.85. Let's see, 46 divided by 20 gives me 2.3. 87 divided by 20 gives me 4.35. Okay, now I have to go through and I have to find this geometric mean. So that's going to be, for this one, I'm going to do 1 times 2. So I'm going to take the round down and the round up, and I'm going to take the square root of it. And here, it's going to be 1 times 2, not 1.2. Try to clear that up for you. Here, it's going to be between 2, because that's the round down, and 3, which is the round up. So it's 2 times 3 and take the square root. Here, it's going to be, take the square root of, let's see, round down is 4. Round up is 5. Okay, and this gives me, let's see, I can just fill it in here. That's like 1.414, and there's more to it. And it's the same for this guy, which is really nice. Here we get 2.4495, some stuff like that. It says round to 3 decimal places. I'll just show a little bit of extra work. And here's 4.4721. Okay, so if it's equal to or above this, it rounds up. If it's less than this, it rounds down. So 1.5 is more than that, so it rounds up. 1.8 is more than this, so it rounds up. 2.3 is less than 2.4, so it rounds down to 2. And 4.3 is less than that, so then when we add it up, we get to 10. We're perfect. If this didn't work, then what we'd have to do is change that divisor. We can change it up or down, and usually you're going to be rounding it down until this is exactly 10.